All right, and good evening, and welcome to the August 16th, 2026 edition of the At Home Planetarium Show. My name is Scott Harris. I'm your host for this evening, and I am very happy to have you either here live with me or viewing later in the recordings. But either way, if you have any comments or questions this evening, please do put those into the comments feed there, and I will do my best to answer those. If you see me looking away here for just a moment, I'm making sure that I can get to those to the comments there if you have them up. Let's try to give me just one moment, and we'll get underway here. Uh, all right. All right, so I should be able to see your chats this evening if you want to put anything into the comment section. And again, if you are watching a recorded version of this, feel free to put any questions in the comments. I'll try to get to those later, or you're always welcome to email me at southernspacerocks@gmail.com. And so this evening, we're going to look at our night sky, and we're going to, instead of taking a full tour of the solar system, we'll have a little abbreviated tour of the solar system using our open space software, and then we're going to concentrate a little bit on the planet Mars. And so we're going to begin where I'm going to come back to you here just for a moment before going over to our Stellarium software. And this is a piece of planetarium software that you can download and use on your own. But I'm going to take you around here at we're at about 8:30 Eastern Daylight Savings Time here in the Atlanta area where I am. And so we'll take a look off to the west southwest, and we will see a bright object in the sky that I have seen posted many times over the last week or so as, hey, is that a UFO? Well, no, it's not a UFO. It's our sister planet Venus there. And I'm going to stop time there so that we can zoom in. And if you have a pretty good telescope, you can take a closer look there and see that Venus is one of those objects there in our sky, along with our moon and Mercury, that because of its position relative to the sun, we get to see it in phases. So we get to see a quarter Venus there. And that is because the bright sunlight is reflecting off the cloud tops that are made of a little bit of water toward the top, but ultimately are very laden with sulfuric acid as you go deeper into the Venusian atmosphere. And those ultimately, those droplets of sulfuric acid are suspended in carbon dioxide, and that carbon dioxide, of course, is the reason for Venus's surface being so hot. It has there's 90 times the pressure at the surface of Venus that you would feel at average sea level here on Earth. It's enough to basically crush you given a little bit of time. But that thick blanket of carbon dioxide has an incredible enhanced greenhouse effect that not only spreads the sun's temperature around the entire globe rather evenly, so it's hot everywhere. You don't really have a nice daytime side and nighttime side that you can retreat to be able to get cool. There is a daytime side and a nighttime side, but you're not going to really cool off on the nighttime side. That intense greenhouse effect raises the temperatures to nearly 500 degrees Celsius and distributes that heat pretty much all the way around the planet. So you're going to see that bright Venus out there. Right now you have the moon nearby, and the moon there in a waxing crescent, headed toward its next full moon at the end of the month on August 28th. And when it is full this time, it will be in a position where the Earth is going to be positioned with our shadow So recently, you may have been paying attention a few days ago, we had the moon's shadow hit Earth and produced a beautiful solar eclipse, totality over Iceland and Greenland and Spain. Beautiful pictures that you probably have seen from Spain. Um, so that was the moon's shadow cast onto the Earth. Now we're going to have the Earth's shadow cast onto the moon in a nearly total lunar eclipse. It's not quite total; it's like 97%, but that's pretty good. So you'll get that classic sort of peach to peach color across the moon, and hopefully you'll have a chance to enjoy that at our next full moon on the 28th. All right, so I'm going to look around the sky here, and if you are in an area where the sun is just setting, you might be able to see a few bright stars. Like one of the earliest bright stars that you could see is Vega, the brightest star in the constellation of Lyra the Heart. Be straight up there at sunset, and there may be a few other faint ones in this type of lighting. So we're going to go ahead and advance time here. We can speed up time and go about an hour into the future, and that way we can go out and really appreciate our sky there. You see Venus is close to setting on the western horizon, and as we come up above that, we'll see the red star there of Arcturus. Arcturus is the brightest star in the constellation of Boötes the herdsman, and if you have a hard time seeing a herdsman there, I don't blame you. What I look for is a kite. If you look here, there is a, let's see if I can use my little tools here to draw. There is a little diamond here. Maybe this time of year you want to think about that as a baseball diamond, although it's a little stretched out. I think of it as a kite, where then the tail of the kite has Arcturus there at its as its decoration. But the ancient astronomers, for whatever reason, saw this as a herdsman, and so if we want to see that better, we can add in the some of the stars here. Let's see if I can may make me erase this in order to gain control of my program again. There we go. We can add in our constellation markers. Still sort of see the kite there, but ultimately add in our artwork and see that we have a herdsman, right? I don't know, the snake's looking at him a little bit suspiciously over here. That is the snake being held by Ophiuchus, the serpent healer. For those of you who pay attention to astrology, you probably know all the stories about how that is sort of the lost or forgotten zodiacal sign. But here's Arcturus that you're going to see immediately above the Venus and the moon as they set tonight. Now, I'm going to get rid of our artwork here and our constellation markers. And I'm going to point out that if you have a hard time identifying where Arcturus is, then you want to do what my astronomer friends always say, which is come over here to this figure that everybody knows. That figure, of course, is our Big Dipper, and there's the handle, and here is the pan of the Dipper. Perfectly good drawing, right? I'm not a great artist when I'm drawing like this. There's the Dipper. That is not a constellation. That is what we call an asterism, simply a star shape. It's actually part of a constellation in this case. But our Dipper there before we look at the constellation, let's look at the fact that this creates an arc. And so my astronomer friends say that you can take that arc and you can create an arc over to Arcturus. You probably already know that you can take the pan here, and I'm going to get rid of our drawings again. You can take the two stars at the end of the pan. You can draw a line out from there, and you're going to intersect Polaris, the North Star. It is not particularly bright. Some people think, oh, it must be the brightest star in the sky. It's not. It is actually about the 49th brightest star, so that's not very bright at all. And before I do any more with that, let me just show you that this is in fact the Big Dipper is part of the constellation of Ursa Major, and we can see that here. and you see the back and the tail and the legs and the body of the great bear. And if you're still having problems, that's why we have the artwork again. Now, if we can use those two stars to find Polaris, North Star, that is the end of the tail of Ursa Minor, the little bear, or the end of the handle of the Little Dipper. You'll see the constellation of Draco the Dragon just above that. And you have if I can get those up here. If we move around, I just want to show you for a moment the importance of that star. Let's go back to having the, we'll get rid of the constellations and the artwork. And if I allow time to advance very, very quickly, you're going to see the entire sky just rotate around as we go through the night. Right? That star stays fixed relatively north, and so it is useful to navigators, certainly in ancient times and even somewhat into the day if you're out on open water. Although GPS kind of takes care of that for you now. All right, so as we move around to the northeast, we can put up I'll put up the artwork this time so I can show you that we have the Queen Cassiopeia sitting here in her chair. We have the hero Perseus below, and his love interest there, Andromeda, the Princess Andromeda, the daughter of Cassiopeia. Of course, in the mythologies, mom was not so nice, and offered Andromeda up as sacrifice to Cetus, the sea monster, who is, we'll see if he's a little off screen right now. I think that's his tail coming up over here. But if we look at this triad here with Perseus, Cassiopeia, and Andromeda, we might be on the lookout for some of the features that you can find associated with those, including this time of year. We just passed the peak of the Perseid meteor shower, so if you're outside in the wee hours of the morning and looking off into the northeast, you might still be able to see a few stragglers from the peak of the Perseids. If I get rid of the artwork here again and I start zooming in on Andromeda, you might start to see a little fuzzy splotch here. That fuzzy splotch is the Andromeda Galaxy, our nearest spiral neighbor at 2.5 million light years away. It's just around the corner, so to speak. That is the most distant object that we can see without the aid of binoculars and telescopes if you're in a very dark sky. If you do have a telescope, though, I encourage you to look at it. Also, if you have a good camera and just want to take a timed exposure shot out in that direction, you might find out that this, one of the neat things you can see is the total diameter of this in our sky is around the same as a full moon. And as we come back here, we can look up a little bit now to the south, and you see the great square of Pegasus, the flying horse that Perseus used to rescue Andromeda. And the great square makes up the body of the horse. Again, we're a little bit into the deeper into the night here. At closing in on midnight, you'll see Saturn rising up above the horizon. And if we, of course, have a telescope that we can take a look at that, we can try to see the rings. And I'm going to stop that right about there. And we are in a position to make out the rings a little bit. You might also pay attention with a telescope for any bright dots that are out around that, particularly over here a little bit to the east and southeast of Saturn. You will perhaps see a bright dot, and that dot is likely to be Titan, the largest moon of Saturn that I often point out as a small planet. In reality, that is the only satellite out there around our planets that has a significant atmosphere, an atmosphere that's actually thicker than our own, made up largely of nitrogen with a little bit of methane, with methane clouds and snow and rain that create a very interesting picture of the very interesting dynamic geologic environment on Titan that we're going to go investigate here in coming years with the Dragonfly spacecraft, a big quadcopter drone the size of a car. All right, so I'm going to come back here a little bit. If you have a really good telescope, you can look over in this vicinity for Neptune. You also see the asteroid Vesta rising. That is the second largest asteroid in the asteroid belt. It's really another small planet, along with Ceres and Pallas and Hygiea. Vesta is neat because it is a basaltic world. Volcanism occurred at some point. It has an iron nickel core. So in a sense, it's a small terrestrial planet. Sometimes you can actually take a photograph of that part of the sky, and if you know exactly which bright dot you're looking at, it can show up in your photograph. As we move around to the southeast, we see the bluish Fomalhaut that is there in the foot of Aquarius. And as we come around to the south, we want to point out the two very brilliant constellations here of Scorpius, the Scorpion, and Sagittarius, the Archer. And I'm going to get rid of the artwork here, and we will take a look at this. And now, have you pick those out? Antares, the brightest star in the claw of the Scorpion, is pretty easy to see. Some of you may know the word Antares means the other Ares or the other Mars. And that is because it looks a bit like Mars in the sky. When it's very close to the ecliptic, so Mars and Antares will be very close to each other at different times of the year, and they very much look like twins there. Antares is actually a red supergiant, not a planet, and quite distant, but very, very enormous compared to our own sun. If you take the body there of the Scorpion and come around to its stinger, that stinger is almost pointing right at the center of our Milky Way galaxy. You can see in a dark sky here the light emanating from the center of the galaxy, blocked by some of the darker, dusty regions. And as we look off toward that center, towards an area that we call Sagittarius star, you might imagine that at the location, we've now verified there's a supermassive black hole that our entire galaxy is basically spinning around. And right next door, right on the other side of that area where Sagittarius star is, the reason it's called Sagittarius star is for Sagittarius, the Archer, and that's because of the constellation of Sagittarius here. You might see his arrow. If you don't see his arrow, perhaps you see a teapot. This is another asterism like the Big Dipper, and if I put in our constellation markers there, it becomes rather obvious that you have the kettle there, the top there on the kettle, and a little spout, and the Milky Way, and sort of is the steam coming out of the spout of the teapot. Now the final thing I'm going to do here is we're going to come around to our we're going to actually zoom out a little bit so that we can see this, and we're going to, well, actually two things. We're going to look up straight, and we're going to see the summer triangle. If you're in a dark sky and just cannot figure out where the Milky Way is, sometimes you can take a time exposure shot, even in a light blue sky, and get a pretty good image of the Milky Way if you know where to aim. So if you don't know where to aim, well, right now, aim, at about midnight, there, aim straight up. But one easy way to find it is, of course, you can find Scorpius, and you can say, okay, well, I know it's in there, now let me go up, but do I go this way or do I go that way? Well, what I can do is I can find this group of bright stars called the summer triangle, and I can find the Neb in the tail feathers of Cygnus the Swan, Altair, the eye of Aquila the Eagle, and Vega is the brightest star in Lyre the Harp, as I mentioned earlier. And just again to kind of verify, you have the Eagle, the Harp, and Cygnus. Well, notice Cygnus has, you can see the wings and the tail and neck, and the Swan is always flying along the Milky Way. And so that's a good way to be able to know exactly where to look in case the light is just too bright for you to be able to see that with your naked eye. Now I'm going to come back here, and we're going to continue looking south, and we see Saturn rising there. And now we're going to go a little bit deeper in the night. We're going to go to 1 o'clock, and we see Uranus rising there. If you have a good telescope, you might see a little mint green disk. And finally, there, if you want to be up at very early in the morning, maybe some of you are getting up already, getting ready for work, you can look out there and you will start to see the two prominent features here. You'll see Orion rising there in the east, and you will see the bright red star. His upper right shoulder is the star Betelgeuse, and that'll be one bright red object, and then just a little bit to the north of that will be Mars. And if we can see Mars with a really good telescope, well, most of the time it's just a kind of a red disk. We can, though, take a little closer look here. Let's see if I can hit the right button. There we go. And occasionally, a good telescope will give you the ability to see a little bit of the ice caps. So there you see the southern ice cap. I believe, no, actually that is Hellas. And so I actually did not stop time there. So we need to stop time, and then I'll zoom in again. Let's see, is that, yeah, that's the Hellas impact basin. I was kind of fooled there. So around the corner, you might be able to catch a little bit of the ice caps. Sometimes you can, in a good telescope, see a little bit of the white. But the main thing you're going to see is either a rusty red disk, or you might start to make out some of the dark splotches here. And these dark splotches aimed at us tonight, shows you the real position of the planet. So if you have a chance to look with the telescope, you're going to see a rusty red disk, perhaps a little dark area near the center. And that northern, from your perspective, toward your north, the northern edge or the western edge of Mars, that dark area is called Syrtis Major. And that is a very old terrain going back almost 4 billion years. And there's a little light area just off the side of it. And it's the boundary between that light area called Isidis, Planitia, the Isidis Basin, and Syrtis, where there's the crater Jezero, where our rover Perseverance has been operating now for many, many years, and giving us great data about the deposits in and along the edges of that crater. All right, so I'm going to come back to you here for a moment. Again, let me check and see if we have any questions out there from anyone. And if we don't, then I'm going to go into our open space program. Now, I'm going to start off here with a world that is not a planet. Looks like a planet. Looks like it'd be a really wild alien planet, right? Well, that is not a planet. That is, in fact, a view. That's a map from data of microwave radiation called the cosmic background microwave radiation that shows us the edges of our observable universe. So our universe, we don't know it's a sphere, and we don't see all of it. There's a limit, but to where we're able to get the radiation coming from the deepest, farthest, oldest parts, that's what we can construct, is this shell around us. And as I like taking a flight in here, and we go from seeing the background radiation to then seeing lots of little bright dots that look like they're together in some kind of giant web. And all of those little dots you're seeing, those bright dots are not stars. Well, they're groups of stars. Those are all galaxies. And we see these big sort of shadow zones because this has to do with the fact that it's hard for us to see things in our own plane of our own galaxy. But these sky surveys, like the Sloan Sky Survey, allow us to then map out the positions of all the galaxies out there, and then ultimately find the position of our own galaxy in our local group. And as we pass toward the spiral Milky Way, we see these two little ephemeral splotches there that are the Magellanic Clouds that you get to really see if you're in the Earth's southern hemisphere. Those are our closest galactic neighbors, but they're just little ghosts of galaxies at this point. And we then can see This is the one galaxy we have to depend on artist rendition of. We can't see ourselves, but we can certainly map out where the stars in our galaxy are and sort of verify that our artist rendition is relatively accurate. So we are in one of our outer spiral arms, and as we speed in toward our own solar system, we get to go by many of the stars that we see at night, and notice that they're very spread out. Those constellations, of course, are figures that we've drawn in the sky. And so that's since we have drawn all those in the sky, they are not all on some 2D plane, so there's actually quite a gap between most of them. So as we're coming in and get about as far away as our nearest neighboring star, which is the Alpha Beta Proxima Centauri system, about 4 light years away, we can start to see the glow of our sun. And as we get closer, we go inside the Oort cloud, which goes about a quarter of the way out to Alpha, Proxima, and Beta Centauri. And if you imagine aliens that were screaming in here for the first time, what would they see? And of course, they're not going to see the traces of our orbits like you're seeing now, just to help guide us. But at some point, you're going to encounter lots of blocky, perhaps little snowball men shaped objects that are out in the outer portions of our Kuiper belt. You're going to start to see some Pluto-like objects that are spherical and very cold, dark ices. But we're going to bypass all that just for today. And as I look at one of the comments there about all those dots you saw before being individual galaxies, yeah, it's estimated there are over 400 trillion galaxies out there that we can document. But we're going to come into our own Earth here for a moment and just appreciate our blue marble out there in space. And we're going to then come out away from that and see the orbit of our moon. And you get to appreciate that the orbit of our moon is quite a ways out there. And this is, of course, had to be in just the right orientation this last Wednesday for the shadow of the moon to be cast onto the Earth in that beautiful solar eclipse across parts of Europe. And as we move out here, I'm going to take a very quick jaunt over to Venus that I mentioned before. And we get to see a world here that is about the same size as Earth, just a little bit smaller. And as we approach Venus, we see that we have this sort of very dull orange color. Now, we also typically see some very wispy clouds, and one of the things that I'm going to show you about OpenSpace, this is a product that you can download. It's a little bit computer intensive, so if you have a slow, low RAM computer, maybe you don't want to try this, but if you've got a pretty good computer, particularly a very graphics intensive one, you can download this. This is OpenSpace. And I'm going to go over to look at Venus here and see that we have see the layers that we're looking at. And so we're going to look here at the color layers, and we want the texture. And you notice that when I hit that, I get rid of the atmosphere. And we look through the clouds using radar like the Magellan mission did back in the 1990s. I was actually like one of the youngest members of the Magellan science team working as a undergraduate at Arizona State back then. And one of our jobs was comparing these features that we saw on the Venusian surface to lava flows on Earth. And so you could see a lot of these bright areas of shield volcanoes here on the surface that had long lava flows extending out from them. And those could be fed by long lava channels or sometimes by tubes. And so we investigated places like Hawaii, Iceland. Even I spent a lot of time in a place in Australia that had very long lava flow called Ondara. And we looked at the mechanics of lavas flowing out here. One of the neat things about Venus is because of that thick thick carbon dioxide atmosphere, we have a very intense greenhouse effect and that very high surface temperature. So when volcanoes erupt, these are basaltic lavas, probably very similar in composition to our own on our seafloor and maybe even places like Hawaii, but certainly our seafloor. Those those basalts erupt out at around 1200 degrees. Well, on Earth, there's a huge difference between 1200-degree lava and you know and 30-degree, even in a very hot area, 30-degree atmosphere. So that lava cools very quickly. On Venus, you have areas that are 500 degrees and 1200-degree lava coming out. Still a big difference. It's going to cool, but it doesn't cool as quickly. So the lava flows are allowed to go out farther away from their source before they totally crystallize in the rock. And I don't want to spend too much time here, but I want to again point out the atmosphere is largely carbon dioxide. Well, where we're going to go now also has a carbon dioxide atmosphere, but the carbon dioxide atmosphere at Mars is very, very thin. Venus is very thick. Again, 90 times the atmospheric pressure at the average surface elevation compared to what we feel here on Earth at sea level. But on Mars, a mostly carbon dioxide atmosphere comes in the form of an atmosphere with only about 4/1000ths of our atmosphere. And again, we see just this orb here, so I'm going to have to go over to our menu, and I'm going to select our layers here. And sometimes it's a little bit rough because of our just the internet speeds and such. So we may use a couple of different products to talk about Mars. But this shows you all the different data that we have. We have visible images from our Mars orbiting camera system on the Mars orbiter. We have the old Viking images from the 1970s. We have MOLA, which is the laser altimeter, which shows you elevation data. We have infrared data with our Themis instruments, and we have these are context images from the very high resolution images on the HiRISE instrument, and we might try to take a look at those. It just depends a little bit on the internet speeds at the moment. But as we look around Mars, the first thing I'm going to do is I'm going to bring you around to the Terminator, in the nighttime side, and this is in current real time, I think, and I'm going to make sure that we're right at the current time. And so if we're looking at the daylight side of Mars, we will be able to see some of the Tharsis volcanoes here. These are volcanoes that are huge shield volcanoes. It's basically Hawaii on steroids. And the largest of the Tharsis volcanoes, many of you are familiar with, and that is Olympus Mons. And Olympus Mons is around here. That covers an area that is the size of Arizona. And again, just for it's taking a little bit for the data to come in here, and I'm going to go over to the what's called the HiRISE context images, and it's going to produce a little bit of a splotchiness, but that's okay because I want to be able to get to some fairly high resolution images if we can get them. If not, I'll show you a different product. All right, so let me go back to that and just get I'm going to get the mock data there from one source and CTX blended, and that may be good enough for what we want to do right now. So here is the, again, Olympus, and we'll see if we can let the high resolution imagery come in. This is literally streaming from the planetary image database. So we have all of the images that are that have been, NASA instruments have collected over decades now, and these are all part of this database, and those images are available. But sometimes it's a lot of data, so it takes a little bit of time to come in. And let's just see what happens. Otherwise, like I said, I may go ahead and show you, the backup plan. Um, you don't get as high resolution imagery, but it's okay. So let me go ahead and do that. I'm going to come out of this just because I'm not getting the imagery I want, and we'll come over to um, a little um, place here. Let's go to, got to get this up on line here with NASA eyes, and I'm going to come back here to a view of our solar system that you can access online with NASA eyes. Now that looks like a mess there, right? And this is again showing you the real time out there in the solar system. And I'm going to first of all come back away from Venus. Took us into Venus there for a moment. So I'm actually going to target Mars, and we'll head in there. And this one has some of our positions of some of our rovers mapped out there for you, which is kind of nice. And I'm going to, just so we can see everything, I'm going to get rid of the shading. And that means that we're not going to have the shadowing from the sun. So we can see some of the spacecraft that are in orbit around Mars there. But I'm going to come back around to show you those ice caps. And let's see if we can zoom in a little bit more there. And this is a little bit tougher to control, but these ice caps are, some people think they're dry ice, carbon dioxide ice, and there can be a little bit of an armoring on them of the, let me get the time controls here so I can turn this completely so it's not moving on me. That's what I need to do. These are can have an armoring of CO2, carbon dioxide ice, but that armoring is over the top of largely water ice. So both polar ice caps are predominantly water ice. And we can come down here to the south, or I'm gonna, let's see if I can get that to not keep having that little thing come up there. So if you need to orient yourself on Mars, here's how to do it. Because I'm looking at this like, what's north, what's south? Well, the thing you do is, again, you want to find, if you're looking through the telescope, you might be confused because you might have a scope that is turning Mars upside down on you. So the thing to do is to find Syrtis Major that I mentioned before. Syrtis Major is this dark splotch here, and is connected to the southern highlands. These are ancient cratered terrains that go back between 3 and 4, even 4.5 billion years old. And that's how you're going to find yourself. If you want that Syrtis Major to stick up, and it's going to be pointing toward the north. And so if I come up to the top, you see the northern ice caps again. And then if I come to the bottom, if you came straight down, you're gonna see, you might get a little bit of light shading, even in a good telescope, from the Hellas Basin. That is the largest impact structure, largest impact basin that is clearly defined. It's not the largest one on Mars by any means, but it is very clearly defined. And then here we see right now the southern ice caps have shrunk, back down to a fairly small right now. And that gives us a chance to see that when the ice sublimates away, you're left with these wild deposits that continue to show you the swirls. And that ice was moving, these are glaciers, and they're moving sediment and leaving that sediment behind in these essentially types of moraines, like we have with glaciers on Earth. And you get to see that swirl pattern. And by analyzing the sediments in those, the layered sediments in those, we've been able to establish a climate record on Mars going back hundreds of thousands of years, so that we can tell, we get some insight into the types of things that might happen that are common in the climates of the planets in our inner solar system, and then those things that are being controlled uniquely by processes on Earth and Mars, and not by astronomical forces that affect our climate as well. So that's a very important aspect of Mars. And as we move along here, we see a lot of the craters. This is a large elliptical impact scar called Orcus Patera. That is believed to be from a very large oblique impact in the distant past. And let me come back around now to those Tharsis volcanoes, because that's what everybody loves those, right? And there is Olympus, and let's see if we can zoom in a little bit here. There we go, and we can see at its summit, it has a large caldera that is where you have material that you have magmas that came up underneath this. They drained away, and the crust collapsed over the top to leave those. We see those same types of features on the big shield volcanoes in Hawaii and other places around the world. And you have tube-fed lava flows that come out all over the place here. This is a giant shield, and it comes down and then comes into a large escarpment, and you can really tell where collapses have occurred of that material that then have spread out across the Martian surface. And I'm going to check back in with my open space program here just for a moment and see if I can possibly get the resolution that I wanted. It is just being a little bit persnickety this evening with the getting in the really high resolution data. So I'm going to try to go to a couple of other sites that I can stream that from, and I'll check on that again because I really want to show you the really high res imagery. Now I want to come back out away from the surface here, and let me go back to Syrtis for a moment, and I will go to the Jezero, again where the Jezero crater is, and our Perseverance rover. So again, orienting north, and we'll come around here to the Perseverance site, and we'll zoom in a little bit on that. Come on there. This one's not as easy for me to control as the open space thing, so that's a little bit of a bummer, but we'll at least get to see where the Perseverance is. And importantly, you see these things that look like rivers that come down out of those highlands. And that's what we believe those are, is back 4 billion years ago, we believe there was stable rainfall, at least at times, on Mars. The atmosphere had periods when it was thicker, with support clouds and precipitation. We had dendritic, tree-like streams that would develop, and those would go out and run downhill and ultimately start to fill some of these basins. The Isidis Basin here was created by a large impact back, again, early in Martian history, probably around the same time that our large impact basins on the moon were created, around 4.1 billion years ago or so. But as that basin was established and water's moving down, water also seems to have moved into a smaller crater here called Jezero, and formed a bit of a river delta. Now, some of us debate whether or not that was a true river or if that was underneath ice, but the bottom line is that you had flowing water either at the surface or underneath a glacier, and where we have flowing water, we're interested in the possibility that life could be there. And so that's one of the jobs of the Perseverance rover, has been to use its chemical instruments to look for traces of ancient life, and also to collect samples that will be available to be picked up in the future if we ever decide to do that. We had a plan to do that. That plan has been eliminated from the budget now, but we hope that that gets to be put back in at some point, because the little canisters are going to be there waiting for us to pick them up and bring those back to Earth so we can get much more detailed analyses of the Martian soils and sediments, and see what was in there back almost 4 billion years ago, and see what's in there today. Most of the Martian surface today we think is pretty hostile, though, because there are lots and lots of very caustic chemicals and minerals that um, would be basically attack anything organic. So even if there were some sort of bacteria that you could imagine being alive near the surface of Mars, the chemistry there would try to extinguish that as fast as possible. So if we have any extant existing life there, we think that would be down deeper inside of the Martian crust. Of course, any evidence of ancient life on Mars could be anywhere in the rocks, but particularly we think back at those times that there was stable water, so that's why we concentrate on those areas that go back to that time period. All right, so I'm going to look over here just for a moment at our open space program. I think I've started to get my resolution in. And let me also check and I want to check and see if I have any questions out there, comments. And okay, but I've got my resolution now on my open space program. And so I'm going to stop that share and I'm going to come back and we'll head into open space and you'll see the difference here. Now we get to see Mons at in more detail. We get to see the just the incredible imagery that our orbiting spacecraft have obtained, and we get to see those caldera in grand and glorious detail. Just aren't those wonderful? And you can see that there are not many impact craters on the surface here, indicating that this must be very young. And how young is it? Well, some estimates put this at as far back as about 200 million years old, but others will go only, some go back to 100 million. Some even suggest there may be younger areas of Mons as well, but certainly it is on the order of no older than a couple 100 million years. As we look in closer, one of my favorite things to look at on Mons are the traces of the lava tubes. And so we can see these collapses over the flowing areas where there's flowing lava. And let's see, and the height of Olympus is, let's see, I can actually call that up. It's not something I automatically remember all the time, but it is about 13 miles high, or a little over 21 kilometers. And so it's a it's a very tall mountain. And in fact, it is it's from across its base is what we often compare it to is the state of Arizona. So if you can imagine the shield volcano the size of Hawaii, well, there are 5 major shield volcanoes on the big island of Hawaii. So now you're going to blow that whole thing up to the entire state of Arizona as one giant shield volcano. These are areas that we have evidence there are caves that still exist. So you can imagine one day astronauts perhaps going and exploring those caves. I used to do that in lava tube caves here on Earth. And as we get in tighter, we start to see that not only are there tubes, there are also lava channels and the lobes of just giant lava flows. You also get to see that there are impact craters there, so this is not quite as young as it might look from staring back at a lower resolution. Beautiful impact craters here, but also great lava channels. And this is just the what it looks like. Imagine this probably does not look that much different than walking around on the Big Island of Hawaii out on the exposed lava flows. Probably a little bit more rusty sand that's covering some of this, but you do get to see these beautiful flow structures all the way out to the escarpment. Here's some festooning that is you get in viscous lava flows like the Pahoehoe flows that you see in Hawaii and other basaltic volcanoes around the world. And I'm going to zoom back out here. We're going to rise up off the edge of Olympus as we get to the escarpment here. And just the escarpment itself is, you see the great landslides that have occurred. And some of this material is has water in it that then is frozen. So there's some evidence that some of these landslides essentially have acted like giant glaciers, what we call rock glaciers, over part of their time. But just to see this chaos here as these landslides have come out. Now around to the edge here, and let me just take a quick look to see if there are if I have any questions out there at the moment. But I'm gonna come. Okay, so I'm gonna come back here to our come back and join you here with open space. I'm going to zoom out and go a little bit over to the east, and so we can see some of those other Tharsis volcanoes. Um, they are smaller than Olympus, but still very high, and also have their own character. Some with very large central calderas there, and again, the striping that you see, if you didn't hear me before, these are little stripes from the high-rise footprints, so you can get in there and get ultra high resolution imagery. But I used to work on volcanoes before working on impacts, and so I could spend all day just looking at these beautiful flow lobes as they come out across the surface. Now, here's a gorgeous complex impact crater. Give a beautiful example of the classic central peak development and terracing. And you might also see that on Mars there are very lobate ejecta patterns that come out around that. Some people believe that that is is a product of having water mixed into the sediments, and so you almost have this muddy material around the craters. But my PhD advisor, Pete Schultz, and some of his earlier students were instrumental in looking at the fact that, yes, this can have water associated with it, but you can also form these without water. You can form them with dynamics in an atmosphere. So perhaps that's an indication of telling you something about the thickness of the atmosphere at the time that some of those craters formed, but it may be also telling you about the ice and the water in there. There are also, you see some beautiful cracks here. These are cracks that are tectonic. These are grabens that from extension of the Martian lithosphere and the crust, the top of the lithosphere. And so you have these beautiful tectonic features. They're not plate tectonics, but they are tectonic features. It means moving a rock. And as they pull apart, the middle there drops down, creating those very sort of piston-like series of valleys and hills that we call grabens for the valleys, and horst for the piston part. And I'm going to zoom back out here and take you around a little farther to the east. And if I do that, let's see if we're going to have to adjust the shading a little bit. Yeah, we're going to have to turn the shading back off here. And let's do that with the, there are two ways we can do this. We can actually do it dynamically here, or we can just change the time. And let me see what's going to be the easiest way to do that. Let's get rid of our shading. There we go. And we'll come around, and I really want this to be bright, so I'm going to change the time. So we're going to go through the Martian day, and we'll get to go into nighttime here. And we see the sun now shining on the opposite side from where we are. But we'll just continue through the Martian day, and we'll get a Martian sunrise. How do you like that? And we'll come across into this region that I want to spend a little bit of time on. There we go. And we'll bring this down here. And as we come down, again, this is off now to Olympus, and the Tharsis volcanoes are around to the west. To the east here, we encounter Valles Marineris, everybody knows. All right, this is deeper than the Grand Canyon by a few times, and it is as long as the United States is wide. And you can really see the landslides on the surface, on the walls of this. Just absolutely gorgeous landslides. And sometimes you see these what are called dark lineae that come out along the walls of Valles, and also some impact craters. It has been considered that these could be some sort of fluid, but a lot of work that has gone into this, including by some planetary scientists at Georgia Tech down the road here, have shown that these, instead, the dark lineae are from essentially, yes, it's like moisture, but it's not like flowing water. It's like wetting of grains in gravity flows of sand. And so, while we were very kind of hopeful that somehow this would be like water running out, it's just the Martian atmosphere is just too thin. Any water that tried to run out on the surface can't stay water. It's just the pressure's too low, so it instantly boils. It doesn't have to be hot to boil. It's just the pressure is so low. And so this is what the walls of Valles look like. Valles, we think, is it's a large extensional tectonic area that is largely created due to the intense gravity loading of the area off to its west there of Tharsis. So you put a huge mass over on in one area, it causes areas nearby to crack. And so you see this area type of terrain here that we call chaos terrain, where these also may have been areas where, as they cracked, water from deeper in the Martian lithosphere could have escaped at some point and fed some of the outwash channels that I'll show you in just a moment. And in fact, as we come around to the east and we get to the end of Valles, we start to see some of those channels that go out across into the lowlands. And those channels, they look like, very clearly branching rivers, right? But they are of enormous scale, and we think that instead of being stable rivers, these were catastrophic floods that are very much like the flooding that you see in the Channel Scablands in Washington and Oregon today that resulted from the collapse of ice dams at the end of the last ice age. And so just enormous, rapid outpourings of water. And you don't necessarily have to have super thick atmosphere to support that. As long as you've got a huge volume of water for a short period of time, it is entirely, that's entirely something that can be supported. And then that water would boil away at the end. But as it's moving along, it is very efficient at sculpting the crust and leaving behind features like these streamline islands, and which you can actually use to tell the direction of flow, with the tapered end being downstream. You erode, like you went around an impact crater here, so it eroded very rapidly on the upstream side, and then the flow detaches going around and doesn't erode the downstream side, and then starts to deposit material on the end of that little island as the flow wanes. So it's a very, very dynamic process, and we think that was active about 2 billion years ago. So, or between 2 and 3 billion years. So basically 3 to 4 billion, you had stable rainfall with a very different atmosphere, and then 2 to 3 billion, you probably had a very thin atmosphere already, but then could have these large outpourings. Now, the reason for the atmosphere changing, we think, is because Mars is small enough that it cooled off enough to lose its, it still has some liquid inside its core, but it doesn't have enough to create the dynamo that we have to create a large magnetic field. There's evidence it did have a pretty strong magnetic field early on that could have protected its atmosphere from the solar wind. Once it lost that, the atmosphere would have just been stripped away by the solar wind. And so now I've come around to, it's a little dimmer in this area, but maybe if I try to see if I can try to keep this together. There's Valles, and now you may notice there's a little bit of darkening here, and then we arrive back at something that looks a little bit more of a subdued color, or a little bit more red, and we're in Syrtis Major now, that dark area I showed you before, and we're over here on the side of Isidus. And I'd like to be able to show you the area of Jezero here with this resolution. And so to do that, I'm going to change time again. Let's see if I can, I don't want to go that way. I want to get this more and more in light, because the way I find, some of the imagery here, I have to find where I'm at because it is a little disorienting when you're trying to fly around. It's like trying to fly a spacecraft around here. Let me change time. I'm going to go just a little bit lighter around to the side here. There we go. Here we are. There's Syrtis. So that is that sort of beige area. That's the darker, older area that extends into the southern highlands. So this very cratered terrain is very, very distinctly older, going back to about 4 billion years, compared to the northern plains that, again, have materials that more like 2 billion years and even younger. But right along the edge here, this is where Jezero Crater is and our Perseverance rover. And the way I usually have to find this is I have to zoom in on this little oblique impact here. Coming a neat little feature in its own regard, where you can tell that this was at a very elliptical crater. So that was something coming in at about 10 to 15 degrees from the horizon. And then just north of that is Jezero, and we will allow a little bit of time to see if we can get a little higher resolution. While that's coming in, I can pan up here to the north, and we can at least see that we have these spidery dendritic patterns. Those spidery dendritic patterns are what we are not like those big outflow channels. These are more like what we'd expect from rainfall. And when you see these dendritic flow patterns, that is indicating that you have stable precipitation over some time. And that comes down kind of joins into larger channels. And then here we go where that water is moving and then establishing a very wide channel here. And then that's coming down into the floor of this crater. Now we're at Jezero, and we're forming this thing that looks like a delta. And again, there are deltas and then there are deltas. There are deltas like the Mississippi River Delta that has a nice bird's foot pattern, which this has. At least it looks like it with the eroded remains of the original structure. So you've got sometimes the water would go over here, sometimes here. This is the result of sediment of water and sediment being carried by that water coming out into a ponded area, into a slack water area as would have existed as a lake in this crater. And and then that building up seemingly a delta over time. Now, I caution you that the same thing can happen with what are called calm deltas, K-A-M-E, under ice. So you could have this water under ice and moving along in a river, and then it essentially developed that underneath the ice. Now, why is that important? Because that ice could be relatively thick and provide greater pressure, so you didn't have to have as great of atmospheric pressure at the surface, just on the overall atmosphere of Mars, if you're getting part of your pressure from the fact that you're under an ice, under thick glacial ice. So exactly what the mechanics of this are, lots of people are working on from the Perseverance data, and again, looking at the chemistry of samples taken along the edge of this delta, because it landed basically kind of out here and then came up along the edge of the delta and then up and is working its way up into the rim there of Jezero to tell us all it can about that period of time back about 4 billion years ago. Now, where I want to end tonight is with some of the evidence for most recent volcanism on Mars. And that someone was asking me the other day about earthquakes here. And we had an instrument called InSight that operated on the surface with a seismometer, and it measured Marsquakes. And those Marsquakes turned out to, some quite large, up over a magnitude 5 quake. And they turned out to be really, there were many of them concentrated in a certain area. And to get there, I'm going to actually turn time backwards here. And I'm going to go around to a little bit of a rough area here that may remind you a little bit of Olympus Mons, but this is a very different area called Elysium. And let's see if we can get over to that here. And sometimes it helps me to, there's another big impact crater there that was at an angle. Lots of impact craters obviously all over the place here. I'm going to see if I can come backwards here and just rotate the planet a little bit because I want to get oriented correctly. So let's bring this around. There's, okay, so got to get north, toward the north. And let's come in here to Elysium. All right, so again, it superficially looks a little bit like Olympus, but it's steeper. And as we come in toward the center of it, there's a very pronounced summit cone to this rather than the big caldera. And some people have said that thought that the steepening slopes here look more like pyroclastic eruptions that you'd associate with big stratovolcanoes. There may be some more evolved magmas here, more silicic magmas. We don't know. I think most of the chemical data we've had from our spacecraft, most of these are still basaltic materials. So rather than being like, Mount Rainier or Mount St. Helens, Mount Pinatubo, this is much more like Mount Etna in Sicily, where we have a large basaltic shield within a steepening summit in what we call a composite cone volcano. And this one is interesting because not only does it show maybe some more evolved magmas than Olympus, so maybe this is something a little bit that is a little bit younger. But as we come down to the southeastern corner of it, we see these dark lines, and these are cracks. And this is the area where many of the earthquakes that the InSight seismometers measured were occurring underneath these fractures. And some other workers were looking at these fractures and noticing that areas around the fractures had wispy deposits, sort of alternating light and dark wispy deposits that they believed were possible pyroclastic eruptions. And here's a great area that you can see those. So these wispy deposits, they envision as being some sort of ashy material that was erupting out, and they have suggested, based on the crater densities and the fact that we still have apparently potentially rising gases underneath, creating some of those earthquakes, that this could in fact be really young volcanism, at least with some type of gaseous pyroclastic flows or pyroclastic eruptions, not flows, but you would have material coming out and then being erupted and then laying down on the surface. Maybe some pyroclastic flow-like material too, but certainly ashy material just being laid down. And it's been estimated that this could be on the order of a few tens of thousands of years old. And speaking of other processes here, as we end up, wind is active on this body, and you get to see that here with these wind streaks around these craters. So this shows you the prevailing wind directions as you have winds taking fine particles and again depositing them, eroding them away from one side of the crater and redepositing them in the wake of the crater on the other side. So I'm going to end our little brief tour of Mars here. I hope you enjoyed it and learned something. Again, if you have any comments here, I'll stay online for a few moments and take a look at our YouTube feed. If you're seeing this later and would like to ask any questions, you can put those questions into the feed, or you are welcome to email me at southernspacerocks@gmail.com, and I will do my best to pick those up and see them. But let me take a quick look here at any of our questions, and with that, I will say good night and hope you join us next time. And be on the lookout at my Facebook site of Georgia Space and Rocks, or as I say, Jasper, kind of like the microcrystalline quartz. And for any upcoming events that we will have, some of those require a small fee, and then others are free like this. And if you have any recommendations for any programming you'd like to see in the future, please pass those along as well, and I'll see what I can do. So with that, thank you for joining me. Hope you have a wonderful week ahead. See you next time.